Hi guys, today we're going to go over section 13.3, energetics of solution. And it just has to do with the energy exchanges going on when you're making a solution. Some solutions, when they form, take in heat. Those are endothermic. And some solutions give off heat. Those are exothermic. So if you have Epsom salt, magnesium sulfate, in your hand while it's dissolving, you'll be able to feel it getting cool, and that's because it's drawing the heat out of your hand and going into the dissolving of the salt. Other things like sodium hydroxide give off heat when they dissolve. You would definitely not want to test that one in your hand. It's very exothermic. All right, so there are 3 parts involved in dissolving a solute. Step 1, you're going to take the solute and split it into its individual parts. And since you are breaking bonds, that process is going to be endothermic, and that's what this is telling us. Delta H is greater than 0. Step 2, you have to take the solvent and separate those molecules and make room to insert the solute in there. So the separating of the solvent, usually water, not always, but usually it's water. And to separate the water molecules, you have to break the hydrogen bonds. So that is also an endothermic process. Lastly, this is called the enthalpy of mixing. That's what delta H mix means. And this process is exothermic because you are taking the solute that is now separate and the solvent that are now separated, and you're mixing them together, so you're forming a bond. So steps 1 and 2 break bonds as you separate these little atoms or ions. And step 3 forms new bonds, so that process is going to be exothermic. Okay, so it's different amounts, different values of step 1, 2, and 3 for each salt. And the balance between the endo and exothermic tells you overall what is the enthalpy of solution going to be. Is it going to be an endothermic process or is it going to be an exothermic process? So the enthalpy of solution is the heat that's going to be absorbed or released when the solution forms. And in order to calculate enthalpy of solution, we have to combine those 3 things we just talked about. The enthalpy of the solute being the solute separating, so that's endothermic. Enthalpy of solvent, change in enthalpy of solvent, is the solvent being separated, so that's endothermic. And the enthalpy of mixing was exothermic. It's going to give off heat. Okay, so we have 2 endothermic processes because we are breaking bonds, and 1 exothermic process because we are making new bonds. Okay, so there are 3 possible scenarios. If the sum of the endothermic is about equal to the sum of the exothermic, so breaking them apart and making new bonds, if these are equal amounts, then delta H is about 0. The increasing entropy upon mixing is what's going to drive that reaction. So we talked about entropy being disorder or the amount of different arrangements that you can have, and that will drive mixing if the heat doesn't. Okay, if the sum of the endothermic terms is smaller in magnitude than exothermic, so if it's a smaller amount putting in and a larger amount given off, it's going to be negative, and that means that the overall process is exothermic. Okay, so this is really important to note. And I'm going to draw that really quickly for you over here. Okay, sorry about that. So this is really important to note that when you have endothermic, heat goes in, and we say that delta H is going to be greater than 0. That means it's positive. Okay, so if something is endothermic, positive with an E at the end. Okay. And it usually, not always, but usually looks like we are going uphill and we are ending at a higher energy than where we started. So this is our delta H. Okay, that's going in. That's endothermic. Exothermic is going to be negative. Okay, exothermic, delta H is less than 0. It's going to be negative. And kind of a mental picture we can see is the enthalpy, the H, would go down, and this much would be released. This would be delta H right here. That would be given off as heat. Okay, and it's kind of like if you have a bank account, if it's endothermic, okay, if you're taking it in, your balance is going to be positive. That's for endo. If it's exothermic, if you're giving off money's going out, then your balance will become more negative. Okay, not quite the way banks work, but you guys get the idea. So exothermic, negative, that's super important that you remember. Endothermic, positive. And I just realized how poorly I spelled that. Sorry, guys. Okay, shh. There's craziness going on right now in my house. Okay, let's switch back to our notes over here. All right, so we have a balance of things going on. If the sum of the endothermic is greater than the sum of the exothermic, the overall delta H is positive, and the solution process is going to be endothermic. So it's just a balance of how much do you put in and how much do you get out. And it's different for each salt. Okay, here are visuals of the endothermic and exothermic processes. So overall, you can see right here, the big red arrow is my overall from start to end, what's happening. This one is going down in energy. So this would be an exothermic process. Okay, the big arrow on the right, the overall process here is going to be endothermic. Okay, and it's a sum of 3 parts. So I know this looks very complicated, but hang with me. This is part 1, okay, where you're separating the solute. Okay, that's the little green one, I believe. It's being separated. And then step 2, you're separating the solvent. Okay, so endothermic, because you're breaking them apart. Endothermic, you're breaking the purple ones apart. And then lastly, this is when you're mixing. Okay, and when you have an exothermic process, you get a lot back and a lot more back than you put in. And so the overall change is going to be that negative. Okay, so when you mix them, you're forming bonds. This last step, you get a lot back. For an endothermic process, you have to put in heat to separate the solute. You have to put in heat to separate the solvent. And when you mix the two together, you get back a certain amount. This time what you get back is less than what you put in. So it's going to be an endothermic process. It's going to require that much energy to be put in to get from point A, where they're separated, to point B, where it's dissolved. Okay? Heat of hydration. Heat of hydration is actually trying to make your life easier. Okay? The heat of hydration meaning it's being surrounded by water. And when you're making the bonds, so we're calling this delta H mixture, right? When you're making the bonds, it's exothermic. What they do, okay, it's a little confusing, so stick with me. To make your lives easier, we're actually combining step 2, right here, separating the solvent, and step 3. And when you combine them, notice that if I put this little arrow for step 2 with the arrow for step 3, I'm still going to get overall a downward arrow from here to here would cancel out, and I still get an exothermic process. So hydration is the separating of the solvent and the mixing of the two, the solute with the solvent. So I'm combining step 2 and step 3 into one thing, and that thing is called the heat of hydration. Okay, over here I'd combine this step with this step, and the overall heat of hydration is how much energy is given off. Okay? So you can see right here as a formula, so my mathematical people will hopefully appreciate this. When you combine the solvent, that's the little water molecules in our example here being separated, so that little part is slightly endothermic, with a big exothermic of mixing them together, you get something called the heat of hydration, and it's going to be a negative. So you put a little bit of the positive, the endothermic, with the big exothermic, and you get this one term. Okay, so from here on out, we're only going to compare to break apart the salt, which is what we're talking about right now, dissolving salts. So to break apart the solute, the salt, compared to the energy you get back when you take the salt and surround it with water. Okay, so this process that is showing up here, we have a positive ion surrounded by the negative parts of the water, and you're forming these ion dipole bonds, all these red dotted lines, and that's going to be giving off heat. Okay, and down here the negative is surrounded by the positive parts of the water, and all of these little bonds are being formed. These intermolecular forces are being formed. Okay, they're not officially bonds, but they are an attraction, and they are going to release energy. In this process and this process, these are called hydration. Okay, so now we're going to compare. We have to break apart the salt, and we have to hydrate the salt. Does it take more energy to break the salt apart than you get back when you hydrate the ions? Or you might only have to put in a little bit to separate them, and you might get a lot back. Okay, so that's what this last thing is going over. This is kind of a summary of how do I know if it's going to be an endothermic or an exothermic process. Okay, and we usually use the word magnitude when we don't want to confuse ourselves with becoming more positive and becoming more negative. Here they've used the absolute value. Okay, so we're looking at the absolute value, meaning the negatives will go away, and we're just comparing the magnitude of these guys. So the solute breaking apart, if it's less than the hydration, the enthalpy of the solute, the enthalpy of breaking the salt apart, if it's less than the enthalpy you get back when they're hydrated, then you're going to have an exothermic process, okay? Because what you put in is less than what you get out. And lithium bromide and potassium hydroxide are examples of that. And you can see that the enthalpy of their solution, when you add the solute and you add the hydration together, the enthalpy of the solution is the total process. It's this red arrow right here. When you add them together, you get negative values. So these are both exothermic. They give off heat when they dissolve. Oppositely, if the heat you put into breaking the solute apart is greater than the heat of hydration or the enthalpy of hydration, then you're going to get positive values, and these are going to be endothermic processes. Ammonium chloride is the salt that's in those instant ice packs. When you pop the little bubble, you're dissolving ammonium chloride in water, and it's very endothermic, so it gets cold very quickly. Okay, if they're approximately equal, the amount of energy required to separate the solute into its constituent ions is roughly equal to the energy given off when the ions are hydrated. Delta H solution is approximately 0. And the process is neither exothermic nor endothermic. And this applies to salt. So if you have sodium chloride, it's positive, but it's positive 3.88. So when you put salt in water, you don't really see any noticeable temperature change. That 3.88 kilojoules per mole is pretty small because we would not be using a full mole of NaCl. Okay, and let's do an example and see if you guys can answer it. The enthalpy of solution for cesium fluoride is negative 36.8 kilojoules per mole. What can you conclude about the relative magnitude of delta H solute and delta H hydration? So in order for it to be a negative total, that means that the energy given off has to outweigh the energy put in. So the delta H hydration, that's our exothermic value, has to be greater than, in magnitude, greater than the heat put in. So delta H hydration is greater than delta H solute, absolute value. All right, I hope that made sense. And we can go over it tomorrow. I hope you guys have a wonderful day, and I will see you all on Thursday.